Hello, everyone. We continue the topic of basic statistics. Today, we come to discuss how to measure the dispersion or the spread of a distribution. So we went through the centrality measures. They define the center, but they do not tell information about the shape. So in order to understand the shape and how the data is scattered around the center, then we need to know about metrics that are used to quantify or measure the dispersion of a distribution. We have a number of them here. We have the range, interquartile range, the variance, and the standard deviation. So we will go over them one after the other. So we start with the range. Basically, the range is the difference between the largest and the smallest value. So since it considers the largest, the actual largest, and the actual smallest, and the data may contain outliers, then this metric is sensitive to outliers. This actually the interquartile range can actually solve this issue. It's less sensitive to outliers since it takes the difference between the third quartile and the first quartile. So here, the interquartile range is equal to the third quartile minus the first quartile. What's the third quartile? Third quartile is the 75th percentile, okay? And the first quartile is the 25th percentile. So what do you mean by 75th percentile and 25th percentile? 75th percentile is the value in which 75% of the data is lower. In other words, 25% of the data is higher, and 25 percentile is the value in which the 25% of the data is lower, and on other hand, or in other words, 75% of the data is higher. Let me just visualize it very quickly here. So assume we have data, okay, samples, okay, so we order them. So we have data samples, we order them based on their value, okay? We order this based on their value. And the one in which this one, the one like in which 75% of the data is lower, the value of that is Q3. Okay, that's the third quartile. We also call it the upper quartile. Okay, and the one in which 25% of the data is lower, the value of that one is Q1. Okay, so in other words, the one in which 75% of the data is higher, and this one, the one in which 25% of data is higher. So actually, we're taking the difference between these two. So we are excluding the upper 25% of the data and the lower 25% of the data, and we consider the 50% in the middle, and we take the difference between Q3 and Q1, the highest point there and the lowest point there. Okay, that's the interquartile range. So according to this definition, then the median is the 50 percentile, right? Because for the median, 50% of the data is lower and 50% of the data is higher. Okay. Now we come back to this. Yeah, this will be a less sensitive to the data, to outliers. We come to next week to the variance. Okay, and here we are defining two variants of the variance. The population variance, when we have all the population, so N contains all the samples, okay, all the elements, all the records. Okay, in that case, we can compute the exact population variance, and it's actually the average of the square differences from the mean. Okay, so so this is the difference between every point and the mean. So we take the sum of those square differences and we average them by dividing by n. So when this is large, then the points are more scattered around the mean. okay? And when this is small, then the points are more dense, more closer to the mean, okay? That this is the population variance. If we don't have if we don't have the whole population and we are exposed to only a limited number of samples, or we are sampling from the population, then we compute what we call the sample variance. So if we have a sample that contains n elements, then we compute the mean of these n elements, and then we compute the sum square differences from that mean for the elements for the different records in that sample. And we take the sum square differences, and we divide here, as you can see, by n minus 1. N is the number of elements in that sample, the sample we picked or the sample we are exposed to. So here, as you can see, we are dividing by n minus 1, not by n. Because actually, this is, first of all, this is a random variable, okay? This sample variance is a random variable because it depends on the sample. So as we sample, as like again and again, we can produce different values for this, okay? So it's a random variable. Second, so this random variable, when we divide by n minus 1, this calculated sample variance is unbiased estimate for the actual variance. That's why we actually subtract this one to make sure this is unbiased estimate of the actual variance. What do we mean by unbiased estimate? So unbiased estimate means like the expected value of this, because as I said, this is a random variable. So if you sample again and again, you are actually producing different values. But as the number of samples goes to infinity, the expected value of this, or the average over the values you produce for this, converges to the actual value of the variance. Okay, the expected value of this is equal to this. In other words, the expected value of the error that you make by estimating the actual variance with this is equal to 0. So it's not biased towards making more positive errors or more negative errors. The positive and negative errors, the above higher and lower values that produces compared to this are equally probable. So this is what we mean by unbiased estimate. So yeah, so maybe let me do this, okay? You remember when we talked about the mean, okay? Okay, if we have let's assume we have a random distribution with mean mu, okay? So you remember when we said, like, when we compute the x bar, okay? Let me just, okay, let me start from here. So when we computed x bar, okay, x bar for a given sample, we sample from the distribution. So x bar is equal to the sum of xi over n. Right here, we divided by n, not n minus 1. Okay, so here we divided by n. So this is the mean for a given sample. So in this sample, we have a number of elements or records. So then we computed the mean. You remember we said the expected value of x bar is equal to mu, right? This is unbiased estimate of the actual mean, or the mean, or the expected value of the random variable. So we said this one, E of x bar, the expected value of this is equal to mu. So the expected value of the average, okay, as we sample again and again, because this is a random variable. As we sample, pick different samples, we are producing different values for this one, okay? So this is a random variable, but the expected value of this random variable is equal to the expected value of x, okay? The expected value of the original variable x, or the mean, the actual mean of that random variable. Let's look at this and prove it. So this is very simple to prove. So actually, the expected value of x bar is equal to what? Is equal to the expected value of sum xi over n, right? We can take 1 over n outside here, all right? and that's equal to what? The expectation of the sum is equal to the sum of the expectation. So we can actually do it 1 over on n sum expected value of xi. Okay. And the expected value of xi is what? So now this is sum from I equal 1 to n. Okay. That's equal to what? That's equal to 1 over n. The expected value of xi is equal to mu. It's constant. So it goes outside, and then the sum from I equal 1 to n is equal to n. Then this is times n times mu. N cancel with n. That is equal to mu. So the expected value of x bar, okay, the expected value of x bar is equal to mu. Okay, so this is unbiased. X bar is unbiased estimate of mu. So in other words, the expected value of the error we make by estimating mu by x bar, the expected value of x bar minus mu is equal to 0. So x bar is unbiased estimate of mu because the expected value of the error is equal to 0. Okay, so if we divide by n here for the sample variance, then actually there's a proof. It's a longer proof. I'm not going to go through that proof for this course, but there's a longer proof shows that actually if we divide by n minus 1, then this will not be unbiased estimate of the actual variance. It will be biased estimate. Okay, there will be a bias there. So that is okay. At the level of 291, this is what you need to know. If you are exposed to the whole population, then you compute the population variance, and this is the population variance. Okay. If you are exposed to samples, then you compute the unbiased estimate of the population variance, which is the sample variance, which this version of the sample variance. Okay. This is unbiased estimate of the population variance. So this is the sample variance. Okay, you divide by n minus 1. Okay, now we come to the standard deviation. Standard deviation is the square root of the variance. Both are telling me the same thing, right? Then you might ask, like, why we need actually both of them. Okay. Okay, so we actually, the standard deviation, okay, why we, maybe the question is why we need the standard deviation, because actually the starting point is to compute the variance, right? And then we take the square root of that. That's the standard deviation. Why do we need the standard deviation? Actually, because the standard deviation is from the same unit of the data, okay? So think of this, for example, this is the voltage and that's the power, okay? Power is equal to V square over the resistance, right? So this is like your data is in the unit of voltage, and this is in unit of power. Okay, so you need to look at some measure that is from the same unit of the data. So you compute the variance, then you take the square root of that variance. So you look at a metric that's from the same unit of the data. So here we come here we're gonna work with this example. So we have a numeric attribute. Okay, we have a number of samples. Okay, for that attribute, and we're gonna compute all these metrics. We start with the range. The range is the difference, as we said, between the max and the min. The max here is 100, and the min is 71. So the difference is 29. That's the range. Okay, so now here we are computing the variance and the standard deviation. So for every point, we take the difference between that point and the mean. So we compute the mean. We assume these are samples from the population. So we compute the mean of these samples, and then for every point here, we take the difference between that point and the mean, okay, for every point, and then we square those differences here in the last row, okay? Then we average them. Okay, so we divide by n minus 1 because we are computing the sample variance. Okay, the unbiased sample variance, the unbiased estimate of the population variance. This one, computing this one. So we divide by n minus 1, which is equal to 24. We got the variance. Then the square root of that is the standard deviation. Okay, the standard deviation is equal to 8.21. Okay, Here we do it with Python. So we hard code the elements of our attribute in this list, and then we convert this list to an NumPy array, and here we compute each one of them. So this is the range, which is equal to the max minus the min. And for the variance, we call the function var, mp.var, and we pass our NumPy as an input, and NumPy array as an input, and we pass this argument. This DDOF stands for data degree of freedom. So this is equal to 1. That means we divide by n minus 1. Okay. By default, this is 0. So we divide by the total number of samples, which is biased estimate of the actual variance. So we here pass the value, pass DDOF equal to 1. So we divide by n minus 1. So we are trying to find unbiased estimate of the population variance. And here, how we compute the standard deviation. We can actually take the square root of that, or we can also call the function std, pass the score and the degree of freedom, and compute the standard deviation. Okay, we got the same numbers. So we generated the same numbers we computed here. Okay, so now we come to the how to find the third and the first quartiles, or the 75 percentile and 25 percentile. So we call the function percentile. Okay, we pass two arguments, our NumPy array. Okay, and here we pass comma separated values in brackets. These values will represent what percentiles we want to retrieve. Okay, so here we define two variables. Then you would expect like we will pass two values here, right? So we're gonna retrieve the 75 percentile in the first variable and 25 percentile in the second variable. Okay, so then we are computing the difference between them. I added this line here to show like you can actually retrieve any percentile you want. And if you are interested in 1 percentile, then you don't need to pass it inside brackets. So here, for example, I want to retrieve the 50th percentile, which is the median, right? Okay. So yeah, this is the way you do it. So if you wanna, this is another way to compute the median, I would say. Okay. So if you print this out, okay. So this is the difference between Q3 and Q1. This is what we are printing out here. Okay. So here, as I said, we retrieved the 75 percentile and the 25 percentile in Q3 and Q1, and then we computed the difference, which is the interquartile range. And this is what we got here. It's 8. As you can see, it's very close to the standard deviation. Okay. So the middle 50% is within 1 SD maybe from the center. Okay. And here is the median. Okay. This is the median I printed out here. Okay. And if you remember, for this specific attribute, we computed the median somewhere up. So I think, yeah, this is the same value we got. So since the number of samples is odd, okay, the median is the one is the value for the one in the middle. Okay. And if the number of samples is even, then we take the two in the middle and we take their average, right? You remember? Or you can just, as I said, you call this, you pass 50 here, you're gonna retrieve the median. Okay, so now we come to box plots. Box plots are box plot is very good visualization tool. So it lets you look at the like with one figure you can extract a lot about the statistics of your data. Okay, for example, looking into this, let's describe it here. So this horizontal line here is actually the lower quartile, or the 25 percentile. This is the upper quartile, okay, or Q3, or the 75 percentile. This is the median. Okay, this is the actual maximum, and this is the actual minimum. And these 2 points here, this one is this one is what we call the upper one, is what we call the upper whisker limit, and this one is what we call the lower whisker limit. The upper whisker limit is equal to Q3 plus 1.5 times the IQR, and the lower one is equal to Q1 minus 1.5 times the IQR. any point above the upper whisker limit is considered an outlier, and any point below the lower whisker limit is also considered as an outlier. So as you can see, looking into this box plot, I can tell like, now this is the median, right? So I can tell like the data here below the median is more dense, here is more scattered, because the number of samples here and here are same, okay? They have the same number of samples because this is the median, right? So, but the data here is more dense and here is more scattered, okay? Let's look at yeah, this is actually for our own data for this score attribute. As you can see here, the median is closer to the lower quartile, okay? The number of points here is equal to the number of points here, but look at this, like the difference between these 2 points, okay? This is a point here, and then there are no values here until this point here. The data is more scattered here. We have only one outlier here from the upper part. We don't have outliers from the lower part. So yeah, we can actually compare box plots. If I have two variables, I can plot the box plots of these two variables, and I can visually look at them and tell if there is any similarity or differences between them, okay, by looking at the positions of different metrics, the median, the whiskers, and so on. So here, how you plot the box plot, okay? So we're gonna do that for our variable score. So here, yeah, we have already explained this. So we have score now stored in a NumPy array. We import matplotlib.pyplot module as PLT. And then here we're calling the function figure. We're specifying the figure size. This is just to define the figure. The actual plotting is happening in this line here by calling the function boxplot. We pass a score as an input. And so here we plot the actual content. Here we are adding a title and we're showing the plot. Okay, this is the plot. This is how we do it with Python. Okay, the height is maybe too much high. Let's do 6. Okay, this is it. The same figure we saw above, right? There's only one outlier from the top, and that's it. So this is our, yeah, it's the same figure we saw in the video. Okay. Yes, we will stop here for today. We will continue next time. Thank you.